Hello everyone, today we're going to be working on example 4-8 and this example is asking us to determine the magnitude and location of the equivalent resultant force acting on the shaft given below. So as you can see, we have our figure right here where it gives us the shaft. It gives us our distributed load, which we know it's 60x squared newtons over meters. Right here, our highest point is 240 newtons meters. And from there, we know the distance or the length, which is 2 meters. So when we're working with these type of problems, we always want to use this equation where the magnitude is equal to the integral of the distributed load. So first thing that we're going to do is we're going to be plugging in things into this equation to solve it. So as you can see, we have our integral. Um, our x starts at 0, so 0, and it goes all the way to 2 meters. So 2 meters. This L is for the length, so how long is it? From there, our distributed load is given to us, so it's the 60x squared times the x. So if we solve for this, we would end up getting 60x cubed over 3. That's from 0 to 2 meters. From there, you would simplify, giving you 20x cubed from 0 to 2 meters. And then if you solve for that, you would end up getting 22 meters cubed minus the second part is basically just 0. And you end up getting that your magnitude is equal to 160 newtons. So going back to the problem, it asked us to determine the magnitude. Remember, this is our magnitude, what we just solved for. And the location is basically our x. So we just determined the magnitude right here, 160 newtons, and for the direction, it's going to be going downwards because as you can see, the distributed load is being applied downwards. So our magnitude is equal to 160 newtons being applied downwards. Now for the location of the equivalent resultant force acting on the shaft given below, to solve for that, we're going to be using a different equation. So this was the equivalent, the magnitude of that equivalent resultant force. And now for the location, we are going to use that the location is equal to the integral of, once again, the length, and x is equal to 0 times x times the distributed load all over our equivalent resultant force. Which is why first you have to determine the equivalent resultant force because you're going to need that for the equation of determining the location. So from there, once again, you're just going to plug in everything. We start at 0, we go all the way up to 2 meters. x times, we know our distributed load is 60x squared, d of x, all over our resultant force. And if you multiply, let's simplify this down a bit more. 60x cubed d of x over our resultant force. This, we solve for it. 60x to the fourth over 4 from 0 to 2 meters over our resultant force. If you solve for this, you would end up getting 62 meters to the fourth over 4. And we just know that that second one is just going to be equal to 0. So I'm just going to write up 0. This is Newton meters over our resultant force, which is 160 newtons. So this, once you solve for that, that should give you that your location of your x is every 1.5 meters. So with that, we are done with our example 4-8, where it asked us to determine the magnitude, which is our resultant force, the magnitude of the resultant force, and the location of the equivalent resultant force acting on the shaft given below. So once again, for the equivalent resultant force, we use this equation right here, and we simply just plugged it in and solved for it. And then for the location, we use this example right here. Please feel free to like this video if you guys enjoyed watching this video, and also subscribe to our channel if you guys would like to see more videos like this.